Hi everyone, thank you Charlie for the introduction. I'll be presenting my work on using polymer chemistry to improve dielectric capacitors, specifically looking at zwitterionic polyimides. I included this slide about me, but Charlie read my bio, so I'll just go very quickly through this. As Charlie mentioned, I have all my degrees in chemical engineering. I finished my bachelor's at Rowan University, and then moved to Drexel University to start my PhD, but then my advisor moved back to Rowan University, become the Dean for the College of Engineering. So I finished my PhD work there at Rowan University in 2024, where, as Charlie mentioned, I was designing polymers that were intrinsically fire resistant to remove the need for these hazardous flame retardants that are typically added. And these were used for structural composites, and I also looked into how specific moieties incorporated into the polymer led to this intrinsic behavior. And now my work focuses on capacitors, which are circuit components that are used to store electrical energy temporarily within an electric field. And these have found use in pulse power applications, such as in pacemakers or in converters or inverters in electric transportation. Now, when we look at capacitors, these are made up of two metal plates that are separated by a dielectric polymer. This polymer is insulating rather than conducting, and it's responsible for the key mechanism by which the overall capacitor is able to store energy. This mechanism is known as polarization, and I'll go a little bit more into detail so that we can understand how these systems work. And so here we look at the cross-section of this capacitor. We have the two metal plates separated by a dielectric polymer. When we look more closely at this on an atomic level, we can visualize these atoms in an idealized sense. We have a positive nucleus that's surrounded by these negative electrons. Now, because these are insulating materials, these electrons are very tightly bound to the nucleus and are not able to move freely when exposed to an electric field. Rather, when we expose this material to an electric field, those electrons are just going to shift away from the electron cloud, creating this dipole moment and aligning the dipole moments within the electric field. And this alignment of those dipole moments is how these materials are able to store energy. If we remove the electric field, that dipole moment will be reversed and no more energy will be stored. Now, this is the key mechanism by how these systems work, and you can see that the polymer plays a very important role in how the capacitors are operated. However, conventional capacitors do suffer from two key challenges, which are both directly related to the polymer that is chosen. Looking first, the first challenge is this low energy density. When we compare dielectric capacitors to other energy storage systems, such as supercapacitors or batteries, we see that they have a much lower energy density compared to those systems. And when we're integrating conventional capacitors, this often leads to very large devices and can cause difficulty in integration. And I'll speak more about this challenge and a little bit more motivation for this in a coming slide, but I want to briefly mention also this other challenge of the low operating temperatures. These conventional polymers, such as the industry standard of biaxially oriented polypropylene, or BOP, are not able to operate at elevated temperatures. We see here the industry standard is only able to operate at about 100 degrees Celsius. And again, I'll talk more about this in a coming slide. And so looking now at the low energy density and how we can maybe address this, we can look at the equation that dictates energy density. We see that the energy density is directly proportional to the dielectric constant of the polymer, or Kaplan. This dielectric constant is a measure of the material's ability to store electrical energy. Conventional polymers have quite low dielectric constants of less than 10, and more commonly they're closer to 2 or 3. So you can imagine if we can increase this dielectric constant of the polymer itself, we can then in turn increase the energy density of the overall capacitor. I also noticed there's another parameter that's directly related to the polymer, which is the breakdown strength of E sub B. This is the maximum voltage the material can withstand before it starts to break down and start to conduct electricity. And so when we're designing these polymers, both of these parameters need to be taken into account. But for this talk, I'm going to be focusing on how we can increase our dielectric constant of the polymer. And one way this can be done is if we look back at how these polymers are storing energy, which is polarization, and this is related to those dipole moments. So it's been shown in literature that you can increase your dielectric constant by increasing the amount of permanent dipoles that are intrinsically part of your polymer itself. So this is one method that I'll be looking into for increasing our dielectric constant. If we look now at this low operating temperature, we have this graph of dielectric constant versus decomposition temperature, where the decomposition temperature is just one factor that affects the operating temperature of these materials. And so looking again at the industry standard above, this has quite a low dielectric constant, but it also has this low decomposition temperature, which is partially limiting its operating temperature. When we look at more higher performing systems like Kapton, which is a polyimide, we do see this slight elevation in dielectric constant, but there is this increase in its decomposition temperature, allowing for a larger operating window. This increase in operating window is necessary because when we're looking at the emerging applications for these, such as in the advancement of the electrification of transportation, we see that we're starting to exceed the upper operating temperature of even Kapton. So there is this precedent of needing to design new polymers that can withstand these elevated temperatures. And so this leads to the goal of my work, is that I want to simultaneously increase both the energy density as well as the thermal resistance of these dielectric polymers. And I propose to do this by focusing on polyimides, which are characterized by having these imide rings shown in purple. Because of the rigidity and high aromaticity of this polymer itself, it imparts high thermal stability to the system, but these on their own do have low dielectric constants. And so I propose to use polymer chemistry to have specific functional groups of the tertiary amines on the backbone of this polyimide, such that we can graft the Zwitter ion groups onto the backbone. These Zwitter ions, which are shown in orange, covalently bond a cation with an anion, resulting in a high dipole moment. This work will combine the benefits of the polyimides, which is the high temperature resistance, with the benefits of the Zwitter ions having that high dipole moment to both simultaneously increase the energy density and the thermal resistance. Now, to create these polymers, this is a three-step process. We first have to focus on creating new monomers. To create polyimides, the reaction is between a diene hydride with a diamine, and I'm focusing on creating new diamines, which will have a reactive primary amine group and this functional tertiary amine group. The next step is to react those diamines with the diene hydride to result in a polyimide structure, and then finally going through post-polymerization functionalization to graft on those Zwitter ion groups. Then with those newly designed and newly synthesized polymers, we can then start to test their thermal stability as well as their dielectric performance. So looking first into this first step of synthesizing these new monomers, this reaction is achieved by coupling aromatic monoamines through an acidic condensation reaction with aldehydes, where we result in our final aromatic diamine, which is named as DMA, that contains those reactive primary groups that will allow for the polyimide to form, as well as those tertiary amine groups that are useful for later on. This reaction was confirmed using proton NMR, but the most important peak is the peak labeled as 5, where this is the hydrogens that is on the carbon that connects those two aromatic rings together, confirming that we have synthesized our monomer. With this monomer, I propose that we create copolymers, where we react two different amines in varying stoichiometries. The first is the synthesized diamine that I just showed, DMA, shown in the green block, and the second amine is this commercially available one known as DMAC, shown in the purple. So by varying the by varying the ratios of these two amines, we can control how much of these moieties is in the final polymer. Now this is important because this allows us to control the final amount of Zwitter ionic content in the final polymer that we're synthesizing based off of how much of this green moiety we have in our polymer. And so I have synthesized a variety of these copolymers with varying amounts of this green moiety with between 0, 5, 15, 25, and 100 mole percent. And these were all confirmed using proton NMR. Now I've also confirmed that these have in fact created polyimides by using Fourier transform infrared spectroscopy, or FTIR, where this top spectrum is for the polyimide and the bottom is for the BTDA dianhydride, which is shown here on the screen. And so there are a few important peaks to point out. The first is this carbon-nitrogen stretch, which is indicative of the imide ring forming. And we do see that that is present in the polyimide spectrum, where it is not present in the monomer. The second peak is the imide ring itself, and again, we do see that that's present in our final polyimide structure. And we can also point out these carbonyl peaks that are in fact present on the monomer, but they shift in the polyimide, helping to support that we are forming our final polyimide structures. And so with our confirmed polyimides, we can then go through this post-polymerization functionalization to graft to those zwitterionic groups onto the tertiary amine groups. And this has been done for the whole series of those copolymers and confirmed using NMR. So now with these new polymers that have been synthesized, we can start to characterize their thermal stability as well as their dielectric performance. And so first we'll look at the thermal stability of these systems. So using thermogravimetric analysis, or TGA, we're able to understand the thermal stabilities of these systems. Looking at the weight percent versus the temperature curves shown in black, where the solid curve is the zwitterionic material and the dashed curve is the non-zwitterionic materials. And this is just a representative curves of the 25 mole percent of that green moiety that I showed previously. The first thing to make note of is that when this polymer starts to lose 5 weight percent, which is a common indication of the onset of decomposition, that the zwitterionic material starts to decompose sooner than the non-zwitterionic one. You see that it's starting to decompose at about 300 degrees C, whereas the non-zwitterionic one decomposes at 425 Celsius. Now we attribute this early onset to the zwitterion decomposing, which is evident in the derivative weight curve shown in red, where we see this new peak that forms in the zwitterionic one that's not evident in the non-zwitterionic material. And this is attributed to those zwitterions starting to decompose before the polymer backbone itself. Now, even though these start to decompose sooner, they do still have the thermal stability that polyimides are known to have, even with those zwitterions grafted on. Now, looking at the relationship between zwitterion content and the thermal stability, we do see at that 5 weight percent loss that no matter the amount of zwitterion content we have, there is still this decrease in the onset of decomposition. And again, that is attributed to that zwitterion being present and it starting to decompose sooner. Nevertheless, the one with the most amount of zwitterion content does start to decompose at 290 Celsius, which is still a good benchmark, and it does still show that it is retaining the thermal stability that polyimides are known to have. Now, we've also characterized the glass transition temperature, or the TG, which is the point at which the polymer goes from a rubbery state to a glassy state. This is important to measure because in application, you want your materials to stay within this glassy state and not transition into a more rubbery state. And so using differential scanning calorimetry, or DSC, we've been able to measure the glass transition temperatures, where this top curve is for the non-zwitterionic material with a TG of about 270 degrees Celsius. This bottom curve is showing it for the zwitterionic materials, and there's no detectable glass transition temperature. These have only been measured up to 275 degrees Celsius, because as I've just shown, they do start to decompose at about 300 degrees Celsius, but we don't want to start decomposing within the instrument. So we do suspect that because there's no detectable TG up to 275 degrees Celsius, that there is this increase in the glass transition temperature when those zwitterions are added on. A similar behavior has been seen in literature, where this is a different zwitterionic material, but the blue curve is for the zwitterionic material, and the red curve is for the non-zwitterionic material. So there is this, this relationship is shown in literature, where once you have zwitterions on your system, you are able to increase your glass transition temperature. So the combination of this potential elevated glass transition temperature and high thermal stabilities do suggest that these zwitterionic materials are able to address that first challenge of the low operating temperature. And so now we can start moving into evaluating the dielectric performance of these materials. However, to do so, we do need to fabricate thin films out of these. And this has been done using spin coating, in which your polymer is dissolved in the appropriate solution or solvent, This solvent is deposited on a glass slide, which is then rotated at a constant velocity to help spread out the polymer solution and evaporate the solvent, resulting in your final polymer in a thin film. So this has been done by increasing the weight concentration of the polymer, and we've been able to create thin films with varying thicknesses up to about 600 nanometers. And this is important because in the next steps, which are currently underway of fabricating these into capacitors, you want to be able to control the thickness of your dielectric polymer between those two metal plates. And so currently we are fabricating these in capacitors and measuring the dielectric constant as well as the breakdown strength to evaluate the overall energy density. And this is being done in collaboration with Professor Pradhan at Jackson State University as well as Dr. Cappelletti at the University of Brussels. And so just some main takeaways from this work is that using polymer chemistry, we're able to create these new zwitterionic polyamides that are showing potential to address two major challenges that capacitors are facing, both this energy density as well as the operating temperature. I've shown that the zwitterionic polyamides do still retain that high thermal stability that polyamides are known to have, and currently it's underway of evaluating their dielectric performance and fabricating these into capacitors. And now tying it back to the bigger picture, there is this potential that we're seeing for these zwitterionic polyamides to outperform the already available polymers that will enable us to advance the electrification of transportation. With that, I'd like to thank both of my research groups, the Priestley Lab as well as the Davidson Lab, my advisors, Ryan Priestley as well as Emily Davidson, and the Andlinger Center. With that, I thank you for your time, and I'd be happy to take any questions.
Thank you for the introduction. Before going to the hard science, I want to show you a photo first. This is a photo taken in the Sal Reservoir in Catalonia, Spain. And you can see that there was a huge water deficiency in the past few years, and this seems to be recurring because the drought is coming back to Spain for the past 10 decades. And in the last year, it finally reached its lowest capacity at 1%, and the local residents are told to limit their water use, and there's no water supply from 10 p.m. to 7 a.m. in that region. I also want to bring you back to 2021 when there is a huge winter storm in Texas where the power outage is so extreme that it's taking more than 200 people's life. So I was fortunate to grow up in Beijing, which is a metropolitan city, that we cannot take the water and energy as what we always have. So we never experienced a life where we opened the tap and nothing came out. Like the people in Spain and like the people there are 2.9 billion people that is lacking of water supply. We also don't experience a water or energy shortage where that we're sharing in cold because there's no energy supply for warmth, or like the 1.2 billion people that doesn't have any energy and are living in the dark. So, since we are having this weather and environment-related catastrophic events, we're having this continuous deficiency of water and energy throughout those years, and this is not getting any better because we are also increasing our water and energy use. So we must find a way to have a resilient water and energy supply so that we can sustain our lives. So I've always been a water engineer, and when it was introduced, my main thesis or my main research is about designing membrane materials for water treatment. Now coming to the Andlinger Center, I start to think more about the connection between water and energy because they're so important and they are so much interconnected. So I'm hoping after this talk I can give you some of my vision on how can we use membranes to address a resilient water and energy supplies for our life. So we are using lots of water. As everyone knows, water is so important to our life, but do you know how much water exactly are we using in the US? I kind of spoil you on this, but take 1 second if you haven't seen it and guess how much water exactly are we using. So the answer is 322 billion gallons of water, and to my surprise, only a very small portion is used in our daily life. So, taking account into the public, domestic supply, and the industrial, it only consists of 19%. So half of the rest actually go into the thermoelectric power plant for cooling and thus for energy use. And the rest are for agriculture and irrigation and thus for our food. So those water, energy, and food and excess really defines our life. This is a tremendous amount of water, and if you count how much water we are using per person per day, and that accounts for 2,000 gallons of water. So where do we find this amount of water that sustains our life? And we need to find it so that we can have food, we have energy, and we have water for our daily life. So right now, 98% of water resources are from fresh water, which only accounts for 3% of the Earth's total water. And by fresh water, I mean this accounts for surface water and groundwater. So those water are very easy to be accessed and they're easy to be treated. However, they are also easy to be disturbed by the weather and our water use. So as many of you know, in the southwest US, we are experiencing droughts throughout the years. And in the recent few years, we are seeing more extreme drought events. However, this drought event doesn't stop in the southwest. If you go to New Jersey, what we are experiencing here, last year there's a severe drought that is also affecting the water capacity in the Honnig reservoir that is supporting 2 million population. So not only in the US, but around the world, like I mentioned, in the South Reservoir. So we really are running out of surface water during this extreme drought event. As we're taking out, or we are having a shortage in the surface water, we need to find other water supplies, and that turns our eyes into groundwater. But you can see from this map that the situation is not looking good as well. So there's an overall groundwater overdraft, and if you see the center of the US, and that's the Ogallala aquifer that supplies 2 million population and 30% of nation's agriculture production, right now we're only at 60% of our water stock. If we keep using water like this and we keep having these drought events, we are going to have only 20% of stock in the next 50 years. So there really isn't enough of fresh water for us to use. And that means we need to diversify our water supply. And we need to look into the rest of 97 of the total water resource of the Earth. So the alternative water source come from whatever is not surface or groundwater, and that means we can reuse our wastewater, we can desalinate the seawater or brackish water, or we can also collect the surface runoff. Just to remind you that the wastewater alone in the US is producing 74 billion gallons every day, and this is already enough for our municipal use. So if we can make use of this water, we can even imagine to have a zero water building where we can withstand weeks or months of water shortage, that we can just recirculate water in the building. And if we have extra water, we can recharge the groundwater that we have depleted to keep our lands there, or also irrigate our crops so we have enough food. So by having all those alternative waters, we can realize more opportunities we have, and also we can have the water that sustain our life quality. However, to use those water, we need to treat them. And as I mentioned, fresh water and surface water and groundwater are easy to treat, but not so much for wastewater and desalinated water. So I want to bring you eyes to what exactly can we find in those wastewater and seawaters. So if you look at the water constituent that is happening in all our water sources, they come in different sizes. You can have a very large size from organic compounds, viruses, to microbes that is often seen in fresh and municipal wastewater. You can also have a very small ions like sodium chloride, and also some toxic metals that are usually seen in industrial wastewater and seawater. So for traditional water treatment technologies, which involves from coagulation to sedimentation, filtration, and disinfection, those can treat those large particles pretty well. But if we do want to make use of our alternative water sources like wastewater and seawater, we need to find ways to remove those ions, and especially those are toxic to human and to plants. So how exactly we're doing that? This is where membranes come in play. So membranes are semi-permeable, meaning that they only allow water molecules to pass through while rejecting all the impurities we don't want from the water that we're treating. And depending on the design of the membrane, you can have different pores on the membrane surface such that they can reject all different sizes of contaminants in water. So for larger sizes, we can have ultrafiltration and microfiltration that is usually used for pretreatment for reverse osmosis and pretreatment for water and wastewater. And if we want to treat the smaller ions, it will come down to nanofiltration and reverse osmosis that usually used for desalination and wastewater reuse. But like any technology, there are some flaws for the existing membrane technologies that we need to tackle so that they are more efficient for our use. Traditionally, membranes are made from polymers that are having an interconnected structure where they're forming a heterogeneous pore volume in those membranes. So you can just think after you boil your spaghetti and strain them and you have different pores between the noodles. So this is how it will look like if you zoom in those membranes. Between those pores, we are letting the water molecules to pass through while rejecting those unwanted molecules. But we also have some defects or some larger pores that we have molecules that are escaping through the membranes. So by having all those transport and interactions between the molecules and the membrane, we have some trade-off between how well the water is permeating and how well we are rejecting the ions. So that brings a limit between permeability and selectivity of the membrane. And while we are rejecting those unwanted molecules, they are kind of concentrating or stick onto the membrane surface. So for the part that is sticking on the surface, we will have fouling on the membrane so that we are blocking the pores for the water molecules to pass through as well. And we're decreasing the amount of water that we are getting from the membrane. However, I want to emphasize the third challenge we have for this membrane, because while we are rejecting those molecules, we're kind of concentrating the water that we're treating so that this will be even more toxic than the water that we are treating. So this is an example of a reverse osmosis concentrate from a desalination plant, and you can see how dirty and concentrated this water is. Treating this kind of concentrate actually adds a huge cost for the water. So for if you calculate the levelized cost of water for RO-treated water, you will have a 25% of cost coming from treating the waste stream that is caused by concentrating a toxic stream. And those toxic concentrate contains whatever is being rejected, and that includes the toxic metals I mentioned before, and also other unwanted molecules. So if we have some materials and some new technologies that can remove the toxicity of the membrane, we can really bring down the price and having it close to the tap water, and we can have more accessible alternative water source for our use. And this is the main reason why I look into nanomaterials, because for nanomaterial, they have some intrinsic properties that may be effective to remove the toxicity from the water. Some backgrounds on the nanomaterials, it is defined as nanomaterial because it is a substance that are between 100 nanometer size and at least in one or the three dimensions. So some of you might already know the well-known graphene oxide is a type of nanomaterial, and similarly, the work that I'm focusing on is using the molybdenum disulfide. So those nanomaterials can come in different shapes. It can be a two-dimensional nanosheets, so just a super thin sheet of the material, and you can stack them together like a lasagna that you have, creating an interspacing between those stacked nanosheet, and thus between those sheets is letting the water molecules to quickly cut through, while it's also rejecting the unwanted ions from water that is larger than the intermolecular spacing. You may also have three-dimensional nanoparticles that you can pack them together and leaving a very small gap for the water and molecules to pass through. And so all of them can have a physical property that is similar to a membrane, they have pores that is defined for filtration and rejecting those unwanted ions. But also you can modify those materials such that they can have chemical properties and reduce the toxicity of the unwanted molecules, like I mentioned in the wastewater. So I want to bring here a case study that I designed the molybdenum disulfide for a specific toxic ion that I want to remove, which is chromium. Chromium is actually widely used in our life. So you can find 80% of the chromium is used for stainless steel to make them stainless, is resisting to any corrosion that is happening. It is also used for metal plating, also for the purpose of anti-corrosion that you can find in automobiles or building materials. And you can also find them in titanium textile as an oxidant, just to remove the impurities in leather and fabric. So chromium have different chemical states. When it's in third state, it is actually a trace nutrient for our body and is much less mobile, so it precipitates naturally in water and is much less toxic to humans. But in some circumstances, when you have a high oxidation state, the hexavalent chromium is actually super toxic and is carcinogenic and have high solubility. So you can have a very high concentration of this hexavalent chromium, and it moves very fast in water that you can have a wide contamination if the chromium gets into either groundwater or surface water. And recently, the California Water Board actually defined the minimum contamination level to be 10 parts per billion, so the allowed concentration is very low. Imagining you have those in your wastewater and it's being concentrated, you can reach a very high concentration, and that really adds the overall cost to treat those waste concentrate. So the benefit of using molybdenum disulfide here is that because this one is very prone to reduction, and MOS2 have a very concentrated electron cloud around the sulfur molecules, we can actually transfer the electron from sulfur molecule to chromium so that it can be transferred to the benign trivalent chromium form. And if we compare the redox potential, you realize that the redox potential from hexavalent chromium to trivalent chromium is actually higher than MOS2, meaning that this reaction can indeed happen and we can use MOS2 to detoxify chromium. So from here, we hypothesize that if we do use MOS2 for the treatment, we can achieve a combined redox reaction and probably also absorption to capture and detoxify those chromium. So like I mentioned, chromium can be reduced to chromium 3. And because MOS2 have a negative surface charge from the electron cloud, it can also be captured and absorbed onto the material surface. So overall, we have a decontamination of our treated water and also securing chromium such that it doesn't leak back into our water system. So we first just want to test our hypothesis for this material. We conducted a batch test, just mixing the material and chromium together. And like what we hypothesized, we did an X-ray photoelectron spectroscopy, and we found that the chromium is indeed being reduced to chromium 3. So we are really achieving a detoxification of the chromium. And second, we also examined its capacity and just seeing how much chromium can we remove per gram of MOS2. And we found out that the removal is much better than other materials because we have this redox reaction between those two molecules. So everything I've done here is in a batch experiment, meaning that they're just floating freely in water and not being on the surface. And this will be very challenging if we want to use that in the water treatment system. So we pack them onto a substrate membrane. So from here we have an MOS2 coated membrane for our use. And not only it have those effects by detoxification and have high capacity, we also find out that the removal kinetics is extremely fast. In those batch tests, it needs this material will need 250 minutes to remove chromium completely from water. But if it's loaded in a membrane, it can done the same job in 0.2 seconds. So this is happening because in a packed membrane, we have a very small pores between the packed MOS2 materials. And in a batch test, the chromium molecule needs to swim a very long distance to get in touch with the MOS2 surface, and with a boundary layer about 50 micrometers. However, when we pack the MOS2 into membrane and have very small pores in between, the diffusion distance for chromium to the membrane surface is only 5 to 10 nanometers, and this really speeds up how fast the reaction can happen between those two materials. So I want to jump out here because I have been talking about water and I have energy in my title and I never mentioned it. But I want to show you how this membrane can be used for energy resilience effort. Like I mentioned before, we are having more and more power outage because of the catastrophic events throughout the years, and this is not getting any better by having this power outage graph analysis before. And this can be represented by the 2021 Texas power crisis that we really need to diversify our energy supply as much as our water supply. I also want to note that although we are shifting to clean energy, we actually don't have enough energy storage devices, and we are wasting a lot of energy that we are generated. So during this power outage, if we have a proper energy storage device, this would really help us to increase the resilience to power outage. To diversify our energy sources, we can rely on different energy generation technologies other than thermoelectric. So that includes solar, wind, and biopower. And as I mentioned before, if we do have energy storage devices, it will also increase the resilience to our energy supply. To build those infrastructures or devices, we really need materials like chromium, nickel, cobalt, and silicon. And those materials are very concentrated in one or two countries around the world. So for example, for chromium, 77% is in Kazakhstan and South Africa. And for silicon, 79% is in China. So if there is any supply chain disruption, we can't really build any of this because we don't have the materials. But fortunately, the wastewater have this solution. And in our recent study, we found out that if we count the wastewater that is being discharged everywhere and just collect all the metals together, there are over 1.8 million tons of valuable minerals that can be found in this wastewater. And just another example of a specific wastewater source, if you go to oil and gas production wastewater, they have 34,000 tons of chromium, and that's nearly 10% of our chromium import. So if we can make use of those materials from wastewater while treating it, it can really diversify both our water supply and energy supply. So fortunately, the membrane I designed can contribute to this a little bit. Remember I told you that after chromium being reduced back to its benign form, we are also capturing on its surface. So we take the spent MOS membrane after reducing chromium and wash with regular membrane cleaning reagent that we have been using every day. And we found out there are 20% recovery of chromium, and from the XPS study, we also see that chromium is being removed from the surface. So this is still not close to 10%, but this proves a concept that we can really use this membrane to both detoxify our alternative water source, but also contribute to a recovery of resources from those wastewater. So to conclude that there are many resources from both water and energy side from the wastewater that if we are treating them, we can also solve both the toxicity problem and also energy shortage problem. And at the meantime, we have 2.9 billion people facing water scarcity, and also the increasingly frequent power outage due to climate shift is really affecting our resilience to water and energy. So by using the membranes, we can really increase our broadening our resource for water and energy supplies, such that we can have a more resilient infrastructure in the future. So to this point, I want to thank my folks in Berkeley, my advisor, Dr. Balshami, and my collaborators, as well as the Kingsbury group in the Andlinger Center and in Princeton. And thank you very much. I'm happy to take any questions.